Okay, cool. Okay, hi everybody. Thanks for coming. Today's speaker is Maya Fishback, who completed her PhD at the University of Chicago with Daniel Foltz, and is currently a NASA Einstein Fellow at Northwestern University. So just a subway right away. Her work focuses mainly on decoding recent LIGO Virgo observations and what they can tell us about astrophysics and the origin of all the events that the gravitational wave detectors have been observing. So without further ado, Maya.
Yeah, thanks so much for the introduction, Derek, and thanks for the invitation to be here today. Yeah, so I'll be telling you about just some of the many astrophysical lessons that we've been learning from LIGO and Virgo's black holes. And so just as a very, very brief introduction to what are these gravitational waves and what are these black holes. So the black holes that I'll be talking about today are in these binary black hole systems. Sometimes I'll also be talking about neutron stars. So in general, I'll be talking about these compact objects that are in these binary systems that are gravitationally bound and they orbit around each other, radiating these gravitational waves. And so these compact binary coalescences are emitting this gravitational radiation, and eventually they get close enough together that they merge. And what these gravitational waves do is they stretch and squeeze matter. And so they cause test masses, the distance between test masses to change. And that's what we can detect with these interferometer detectors, such as LIGO and Virgo. And so we now have this network of gravitational wave observatories. There are the two LIGO detectors in the US, the Virgo detector in Italy, Kagra, which just came online recently in Japan, and coming soon, LIGO India will join the network. So the great thing about all these gravitational wave detectors is that they're observing a lot of gravitational waves. The rate of discovery has just been accelerating pretty dramatically. And so the latest set of these gravitational wave detections is in this GWTC3, the third gravitational wave transient catalog. And in this poster here, you can see each one of these panels represents one gravitational wave detection from one of these compact binary coalescences or these merging black holes, or sometimes merging neutron stars, or in a couple of cases, also a neutron star merging with the black hole. So altogether, there are around 80 of these mergers that have been observed to date. And so taking all of these detections together, there are a few questions that we want to answer and that we're starting to be able to answer having so much gravitational wave data. And the first thing is just figuring out how are these black holes made. So we know that one way that the universe makes black holes is through massive stellar evolution. These black holes can be the remnants of very massive stars. And so in this plot here, which is a very simplified diagram that includes a lot of things that we don't know about massive stellar evolution, but the basic picture is that if you have stars that are around 9 or 10 times the mass of the sun or bigger, at the relatively low masses and at high metallicities, they'll end their lives as a neutron star. If you get even more massive stars at lower metallicities, they'll end their life as a black hole, either through a supernova explosion that then there's material falls back and creates a black hole, or a direct collapse of a black hole or a failed supernova. The other thing that we want to understand is that all of the black holes that we're observing in gravitational waves are in these pairs. We only observe binary black holes. And so we want to understand how binary black holes are made. So this picture can get even more complicated than just understanding how individual stars give birth to individual black holes. There are kind of these two main channels that people consider. These are kind of umbrella channels. There's a lot of different sub channels within them. The first one is this isolated binary evolution, where you basically start off with two stars in the galactic field. They live their life, they evolve. The more massive star usually lives faster and dies first. It maybe explodes as a supernova, leaves behind a black hole. Then you have this second star, which maybe explodes as a supernova, leaves behind a black hole. And then you have two black holes that are maybe still gravitationally bound after all of that. And maybe they're actually close enough together after all of that that they can merge within the age of the universe, which is quite challenging, right? Because you want these two black holes to be close enough together at this stage so that they can actually merge through gravitational radiation. But you don't want these two stars up here to be too close together, because as stars evolve, they expand. And if they're too close together, one of the stars can swallow the other one, and you won't have two stars anymore. So there's a lot of kind of complicated astrophysics that can happen in this broad channel to make that happen. The second broad channel is the dynamical channel, which is just an umbrella term for anything where you have more than just two stars, more than just two black holes. Like in a dense star cluster, such as a globular cluster, you can have a lot of stars in the center of your cluster. They will evolve, create this group of black holes in your cluster that will interact with each other dynamically and can dynamically assemble binaries that are tight enough to, again, merge within the age of the universe. So kind of taking an even step back from that, another thing that we want to understand when looking at all of these gravitational wave observations is kind of the cosmological context for these. So what are the environments that these mergers happen in? At what time during the age of the universe do they merge? And how does that fit in with what we know about the evolution of the universe, with what we know about the evolution of stars across cosmic time, with what we know about galaxies and how they evolve, large-scale structure, what we know about the expanding universe. So kind of this bigger where and when context for these mergers. So kind of putting all of these different questions on one slide, there's a lot of aspects of the origins of these black holes that we'd like to understand. So what were their progenitors? And I mentioned that one way our universe makes black holes is through massive stellar evolution. For the rest of this talk, I'm going to assume that all the black holes and neutron stars that we've seen are the end states of massive stellar evolution, although there are other ways that our universe might create black holes, such as primordial black holes, which are very exciting. But I won't really talk about that further. The second thing that we then want to understand is when and where did these massive stars live? So if these black holes are really allowing us to probe massive stellar evolution in this new way, when and where did these stars live? And then how did they die? Did they explode as a supernova? Did that supernova have a kick? It left the compact object. Did it leave the compact object with a spin? Was there no supernova explosion at all, a failed supernova? Then we want to understand, how did these stellar remnants pair up into merger partners? So did they spend their whole lives living together in this binary system, or did they find each other through dynamical interactions? Or some combination of the two? It was a part of the triple system. And then we want to understand, how did the resulting mergers affect their environment? So if it's two black holes that merge, they probably don't have a big effect on their environment. They're really just emitting gravitational radiation. But if there's a neutron star involved, it could create this big explosion as this dense nuclear material interacts with other dense nuclear material, it gets ripped apart by a black hole. And that can lead to very exciting signatures outside of just gravitational waves in the electromagnetic spectrum, and also may create some of the heaviest R-process elements in our universe. And then we want to understand this context of how is the universe evolving over the history of these black hole mergers, and what does the history of these black hole mergers, how does that connect to things like galaxies and stars throughout cosmic time? So all of these pieces of the story of making these gravitational wave sources are going to affect the observable properties of the gravitational wave events themselves, and often kind of subtle ways. So a lot of what we try to do is go from these gravitational wave observations to going back and figuring out this complicated history. And so when we observe binary black holes and gravitational waves, we can learn a few things about the system. We can learn how big is each black hole. So what are the masses of these two black holes? The bigger of the two black holes is labeled as M1, the primary mass, and then the smaller one is M2, the secondary mass. This has the largest effect on the gravitational radiation. It affects the evolution of the orbital evolution at kind of high separations. So this is really to first order what we can learn from the gravitational wave observation. To some extent, we can also learn about the spins of the black hole. So how fast is each black hole spinning, and then where are those spin axes pointing? So with respect to each other, but also with respect to the orbital angular momentum. So are they pointing in the plane of the orbit? Are they aligned with the orbital angular momentum? That's something that we can learn from the gravitational wave signal. Then the other thing we can learn is, where did they merge? So on the sky, especially as we get more detectors, we have better localization, so we can get some idea of, what 10 or 100 square degree patch of sky did this merger happen in. But we also get the distance to the source from the gravitational wave signal. We actually measure this luminosity distance. We don't measure redshift directly from the gravitational wave event, but for this talk, I'm going to assume that there's a known relationship between distance and cosmological redshift, assuming that we know the background cosmology perfectly, and kind of use distance and redshift and look back time interchangeably. So all of these pieces of all these observables, we can piece them together and try to learn about how these black holes are made. So we have all of these kind of events that you saw in that poster, with each panel with kind of one of these chirps, these gravitational wave detections. For the rest of this talk, I'm going to talk about what we can learn from a population analysis. So taking all of these single events together and trying to learn about the population statistics. And when we do that, a first step that we do is to introduce some kind of population model. So this population model is going to describe the distributions of masses, spins, redshifts across multiple events. So we're not too concerned anymore with what are the masses of each individual gravitational wave event that happened on a given date. We want to know what is the overall distribution of those masses. And so an example of that is to fit a power law to the black hole masses. So then we want to know what is the merger rate as a function of black hole mass, black hole primary mass. And in this model, there are a few parameters: the minimum black hole mass, the power law slope, and the maximum black hole mass. So these are now the parameters that we might try to measure. And to do that, we need to take into account measurement uncertainty and selection effects. And so measurement uncertainty, probably a lot of people have encountered that in many other contexts. That's just, we can't perfectly measure the mass of any given event. We know that it's somewhere between 15 and 25 solar masses. And selection effects, I'll just show you one example of selection effects. And this is actually the biggest source of selection effects for gravitational wave observations, is the selection effect as a function of the mass of the binary. And so in this plot, the y-axis is showing the sensitive volume as a function of the total mass of the binary, and the different colored lines are just different mass ratios. But what you can see is that this sensitive volume increases pretty steeply as a function of the total mass. So the more massive events, they emit intrinsically louder gravitational waves. We can see them, hear them out to a larger distance. And so we're probing a larger volume of the universe to those more massive events. And so what this means is that the more massive events are just overrepresented in our catalog compared to their astrophysical occurrence rate. And so I'll come back to this example soon when talking about the mass distribution. So for the rest of the talk, I'll be talking about a few different astrophysical lessons. The first thing I'll talk about is the mass distribution. And for the mass distribution, I'll be focusing on mass gaps. The first mass gap I'll talk about is this upper black hole mass gap. So this is the exact same plot that I just showed before, but now I've highlighted this region above total masses of around 80 solar masses. And the point here is that I just argued that the sensitive volume is much higher for these more massive black holes, but in the first two observing runs of LIGO and Virgo, when we had 10 binary black hole events, we had a handful at total masses of around 20 to 30 solar masses, a few that had total masses of 60 to 80 solar masses, but sort of right above 80 solar masses, we had this notable absence of events, even though we're way more sensitive to these events up here than the ones down here. So from that, we concluded that these systems must be rare in the underlying population. Otherwise, we would have detected them much earlier. And to make that more quantitative, what we did is fit this population model to the black hole mass distribution. So this same kind of power law that I described before, we fit this 3-parameter model to describe the primary black hole masses that had a minimum mass, some power law slope, and a maximum mass. And what you see here are all these purple lines show 500 draws from the posterior on the mass distribution inferred under that model. So you can see that most of these posterior draws cut off. There's a maximum mass at around 40 solar masses. There's a handful that go up to 50 or maybe 55, but that's really only a few in 500 probability that we inferred that the maximum mass was that high. So we were pretty confident that under this model, the maximum mass of black holes was 40 solar masses. And this seems to fit the data pretty well, just there being the sharp cutoff here. And this was very exciting because it really was this clear observational signature that almost perfectly matched theoretical predictions for being the lower edge of what's known as a pair instability or a pulsational pair instability supernova mass gap. And the idea here is that when you have a very massive star where the carbon oxygen core of that star is between around 40 and 120 solar masses, that star becomes unstable. What happens is that that core of the star is very hot, and the photons that would otherwise be providing pressure to counteract against gravity start to spontaneously produce these electron-positron pairs. And so the photon pressure support is gone, the star suddenly contracts and violently ignites this explosive oxygen burning. That oxygen burning can either disrupt the entire core of the star so that there's no black hole left behind at all. The whole star just disappears in this big parent stability supernova explosion, or it's energetic enough that it leads to this these pulses where each pulse can shed up to 10 solar masses of material from the star. And so the star loses a lot of mass through these pulses until it collapses to a black hole that's safely below this 40 solar mass cutoff. And so this process had been theoretically predicted since the 1960s, that there should be this parent stability supernova that leads to an absence of black holes in around this mass range, between around 40 and 120 solar masses. So we really thought that this maximum mass that we were seeing here was really consistent with being the lower edge of that mass gap. Of course, this idea of a mass gap only applies to black holes that are formed from stellar collapse. So that's kind of one caveat. And then another caveat is that there are theoretical uncertainties in where this mass gap should be due to things like nuclear reaction rates, which determine how much oxygen compared to carbon is in the core of your star. So that can shift the edges of the gap a bit. The structure of your star. So this theory is kind of, there's a pretty good mapping between the mass of your carbon oxygen core and the mass of the black hole, but kind of how much of the envelope you have. If you are holding onto your hydrogen envelope, by the time this happens, you can dump potentially extra mass onto your black hole. Additionally, if you have, beyond standard model physics that manifests in the cores of these stars, that can also add as an additional source or sink of energy that can change where this mass gap is. And then of course, if you have black holes that are formed not from stellar collapse, those may populate the gap. So as a kind of simplest example of this, we already knew from the very first detection by LIGO that when you have two 30 solar mass black holes, they merge, they formed a 60 solar mass black hole. That 60 solar mass black hole is technically in this mass gap, but the question is, can that black hole go on to merge with another black hole and participate in an additional merger? But that's definitely something that we are actively looking for in our data signatures of these repeated hierarchical mergers. And so one kind of detour about that is that another cool thing about this formation channel where you have black holes formed from smaller black holes is that in addition to producing more massive black holes, it also leaves this kind of distinct signature on the spin distribution of your black holes. So here you can see these different curves are showing different probability distributions on the black hole spin parameter, this dimensionless parameter between 0 and 1. There are a few different curves here corresponding to slightly different scenarios, but the point is that they all peak at a spin parameter of around 0.7. And so when you have these black holes that are born from previous mergers, they'll tend to spin at around 0.7. And so that's an additional signature that you can look for to disentangle whether your black holes are formed from stars or from previous black holes. Okay, so everything that I told you kind of about, we found this maximum black hole mass at 40 solar masses. It was this very simple power law mass distribution with a sharp upper mass and lower mass cutoff. That was all just based on the first 10 events. And I told you, like on my third slide, that we have 80 of these events. And so unsurprisingly, we've learned a lot more than just what we learned from those first 10 events. And one relevant example is this first detection, GW 190521, of two black holes. One was around 85 solar masses, the other one was around 60 solar masses. The 85 solar mass black hole, even with its kind of large measurement uncertainties, it's definitely inconsistent with being below 40 solar masses. So it's definitely not part of this population that we measured before that has a maximum mass at 40 solar masses. It's not at all, it's much more massive than that maximum mass. And it really seems to lie within this mass gap. And you can see here that a lot of us and a lot of other people as well in the public were very excited about this. There were headlines, these black holes shouldn't exist, but there they are. So they're talking about this kind of forbidden region of this pair instability mass gap where we now confidently detected an event. And so in addition to just that one event that seemed to be in the mass gap, it's not the only one like that. There's actually a population of these big black holes with masses above that 40 solar mass limit that was revealed in the third observing run of LIGO and Virgo. So these black holes are very rare in the population, kind of our simplest conclusion that systems with total masses above 80 solar masses are rare still holds. They only represent around 1% of the underlying population. But because we have these selection effects to detecting more massive systems, we're able to see a population of them in our data. And so that simple truncated power law model that was fine for the first two observing runs, now with data from the third observing run, we know that the mass distribution is more complicated. So one way to make it more complicated that still fits the data is to add this Gaussian peak on top of the power law. So you can see that there's kind of this excess of black holes between around 30 and 40 solar masses, after which the mass distribution falls off more steeply. There are kind of two different curves here corresponding to our inference based on the first half of the third observing run and the second half of the third observing run. But the general picture is still the same. And so that's kind of the only thing we can say observationally, is that the mass distribution is more complicated than just being a power law that cuts off at 40 solar masses where the parent stability mass gap starts. We don't actually know where these big black holes are coming from, how they're made. So it's possible that, you know, there is some underlying mass distribution that cuts off at around 40 solar masses, and then we have this subpopulation of black holes that contaminates the mass gap, like maybe they're made in a different formation channel, like they're actually made from smaller black holes. So that is one possibility. There's no kind of smoking gun signature for that yet, but it's definitely a possible explanation. It's also possible that what we're seeing here is this kind of tapered lower edge of the mass gap. Like maybe there is a mass gap that starts at around 40 solar masses, but sometimes, you know, you can dump additional mass onto your black hole because of fallback of the hydrogen envelope, or your star is more complicated because it itself is a stellar merger remnant product, or something like that. It's also possible that, you know, we were just, before we measured a sharp cutoff at 40, that wasn't the full picture. That has nothing to do with the parent stability mass gap, and that the parent stability mass gap only starts at around 80 solar masses, or somewhere where we actually have observed 0 events. And, you know, that would, I think, imply something pretty extreme about our understanding of stellar evolution, like the nuclear reaction rates we're using are pretty far off, or maybe even there's new physics. Okay, so that's what I wanted to say about this upper black hole mass gap and parent stability. The next thing that I'll talk about is this potential mass gap between neutron stars and black holes. But also, I should say, I don't know if people are allowed to interrupt with questions, but I'm fine with that. Okay. Oh, yeah.
Well, just because it would be really nice to discuss mass instead of moving on
Yeah.
to the previous slide. Should I interpret this adding of the peak of the Gaussian peak to the population analysis as we think there is a population or some population of black holes that behaves this way? So, you know, are the black holes that are violating this 40 solar mass cutoff kind of the tail of this population, if you will? Or is it, this is just what fits the data best, and you're agnostic about the underlying astrophysics?
Yeah, that's a good question. And I definitely encourage people to also check out this collaboration paper, which many people here also contributed a lot to, because there are kind of other mass distribution models that are considered. The basic shape of all those mass distributions in terms of merger rate as a function of primary mass is pretty similar, but whether you interpret this, and it's the basic picture that there is a higher merger rate, a significantly higher merger rate between 30 and 40 solar masses compared to above 40 solar masses is still true. But whether this is actually a peak or not is, you know, we think there's a peak there because this also holds up with other models, but most of the models we've considered have some kind of peak feature. And so it's, yeah, to some extent, this is a choice that we've made in this model. And this model was actually first proposed by Colm Talbot and Eric Thrain. And the idea for a peak here was meant to catch the excess of black holes that might be pushed down through pulsational parent stability supernova. So they thought, okay, there might be this excess, but in that model, in their kind of original paper, they thought, okay, there would be this excess, but then it would be followed very quickly by the sharp cutoff. Kind of you have the lower edge of the parent stability gap, and then everything that would have been inside the gap now loses just enough mass to be right below the gap. So that was like the astrophysical motivation. It doesn't really match what we're seeing because we are seeing like a much more extended tail. So it's still, you know, possible that this excess here is related to pulsations from parent stability, and there is some cutoff here, but then we're being contaminated by another population. But yeah, this actual form of the mass distribution is very, very loosely astrophysically motivated. It's really just kind of like, we started with a power law, that doesn't work. Let's fit some additional stuff to make it fit the data well.
Right, because like adding hierarchical mergers, then it just becomes even more complicated. So just, I think deconstructing it as power law plus peak makes it feel like it's some things are power law, some things are peak, but that's really not the story, right? Yeah,
I think it's probably more likely that there's like a power law plus peak and then another power law or something like that. Okay. Cool. So yeah, let me just talk a bit about this other mass gap. So this other mass gap used to be a lot more famous than the parent stability mass gap before we had any gravitational wave events, because the idea for this mass gap was motivated by electromagnetic observations of neutron stars and black holes, mostly in X-ray binary systems. And from observing X-ray binary systems, you know, we kind of know that the maximum neutron star mass has to be below 2.5 solar masses or so. And the minimum black hole mass, it seemed that it started at 5 solar masses or above that. So it didn't go, we didn't have any black holes that were right above the neutron star maximum mass. You can see now there are other candidate electromagnetic observations that might be within that gap. Some of those have kind of been some of these are not really believed to be black holes anymore. But anyway, there still could be something interesting between the maximum neutron star mass and the minimum black hole mass that would tell us about the supernova explosion mechanism, for example. We don't necessarily expect the transition between neutron stars and black holes to be very smooth, or the minimum black hole mass to line up with the maximum neutron star mass. And it's interesting because when we look at all of the gravitational wave events, you can see that we have a bunch of binary black holes. So each one of these curves here shows the primary and secondary mass contours on that event that we infer from analyzing the gravitational wave data. So you can see we have a bunch of these binary black holes. We have a couple of these binary neutron stars. We even have some neutron star black holes where it seems that the primary mass is above 5 and the secondary mass is below 3. And in this paper led by Amanda Farah, she fit a population model to all of these events. And one thing that you can see just from looking at these masses is that we don't really have events that are filling in this low mass gap. So it's kind of interesting, especially thinking about the neutron star black hole events, because we have these binary black holes, as you can see, most of them really prefer to be symmetric with M1 equals M2. Same is kind of true for the binary neutron stars. And it seems like these neutron star black holes are kind of avoiding this M1 equals M2 line. It kind of seems like they're straddling the gap in some way. And of course, this is all super hand wavy. You should just squint at the data and draw conclusions from that. You should actually do the proper hierarchical analysis where you fit a population model. So that's what Amanda did. This is showing the mass distribution as a function of primary mass. It only going up to 10 solar masses in this case, but this model included all of the events from the first half of the third observing run plus the neutron star black holes. And basically what we learned is that there's some deviation from a power law. Basically, if you fit a power law model to the black holes and try to extend that down to neutron stars, that doesn't work. So there's something going on between the neutron star, what we think is the neutron star maximum mass, and the black holes. Here is a fit that's a broken power law plus a dip, and this is actually mildly preferred by the data. So it seems that the data is telling us there may be some dip here between neutron stars and black holes, but we don't really know. All we really know is that there's some deviation from a power law at around 2.4 solar masses, which is interesting because maybe this actually coincides with the neutron star maximum mass, although kind of a priori, we have no reason to expect that it would. We don't know that neutron stars exist astrophysically up to the neutron star maximum mass. This feature that we see here probably should be there, but it might not line up exactly with the neutron star maximum mass. But this is also kind of an interesting way to learn about neutron stars and black holes and the supernova explosion mechanism. Yeah.
In this plot, what's the difference between the black traces and the green trace?
Yeah. So the black traces are all draws from the posterior, and the green one is the maximum likelihood trace. And you are then probably wondering, why are all these black ones kind of above it?
Yeah.
And that's because the prior for this, the depth of this dip is flat between like 0 and 1. And the maximum likelihood is kind of at the edge of that prior. So we infer that the dip, like the maximum a posteriori value, is kind of for a pretty steep dip, or like a relatively empty-ish gap. but there's a lot of prior volume for less empty gaps that are kind of showing up here.
Thank you.
Okay, so that's all I wanted to say about the mass distribution. If there, oh yeah.
Yeah, you go back to the slide. Super interesting. Just out of curiosity, does this look any different, or is there a reason to expect this to look somewhat different if you did the distribution in total mass in the system? Like, would it be about the same? I mean, just looking at that plot, it seems to be like strong correlation between the mass of the two pairs, so maybe it wouldn't add a lot more information, but like, could you get anything else from looking at the distribution in total mass rather than primary mass?
Yeah, so when we do this population fit, we're fitting both, like for both masses. So the primary mass distribution and the mass ratio distribution, we thought it was more natural to look at things in terms of mass. So actually in this model, we're fitting for like some underlying mass distribution and then a pairing function. And we thought like the component masses might be a more natural way to try to look at things, because then the feature kind of corresponds to features in those component neutron stars or black holes rather than the total mass. But yeah, the actual fit is like we're fitting for some population density over this M1, M2 plane, like the rate at each M1, M2. And so you could marginalize that over the total mass dimension and look at it in terms of total mass also.
So that second plot is margin, like there is some hidden variable that we can marginalize.
Yeah, exactly. Okay, cool. So next I'll just say a couple of things about the spin distribution. The first one is about spin tilts. And when thinking about spin tilts, what a lot of people do is consider this effective spin parameter, chi effective, which is the effective in-spiral spin, which is approximately conserved during the gravitational wave in spiral, and it's well measured from the gravitational waves. So often it seems from looking at individual events that the only thing we can say about spin for individual events is through this effective spin parameter. And what this effective spin parameter actually is, it's this mass weighted average of the component black hole spin part that's aligned with the orbital angular momentum. So we take the part of the spin vector that points in the direction of the orbital angular momentum for each black hole, and then take the mass average of that, and that's this chi effective. And sorry for the confusing notation here. Chi, earlier I used A to refer to the dimensionless spin. It's the same thing. A and chi are the same. So the idea here is that if your spins are never tilted by more than 90 degrees, so if they're never kind of pointing in the opposite direction as the orbital angular momentum, your effective spin parameter will always be positive. And this is interesting because we think, again, going back to that very early slide I showed in that cartoon by Shanika, that in the field scenario, you would have small misalignments. Your black holes would be sort of aligned with each other and with the orbital angular momentum because those stars have kind of aligned their own spins. On the other hand, if the spin tilts are isotropic, so if the tilts are just randomly distributed, which we would expect if those black holes are just randomly encountering each other in some dense star cluster, this chi effective distribution will be symmetric about 0, because cosine theta will just be uniform between -1 and 1. And so what we've learned from the distribution of chi effective is that if you look at this cumulative distribution function, which just shows what's the fraction of systems that have chi effective below some value on the x-axis, if things were isotropic, we'd expect half the time chi-effective to be negative and half the time chi-effective to be positive. This kind of here at the intersection of 0 and 0.5, that's ruled out by our inference. So we know that the chi-effective distribution is not symmetric about 0. We know that the spin tilts are not isotropic, they're not random. There's actually a preference for positive chi-effective. You might then also see here that if you look at the 0 line, if there were no systems with negative chi-effective, this 0 axis, y-axis would cross 0. That doesn't seem to be the case in this model, but there have been people that have argued that this very tiny number that you see here, which is consistent with being the minimum chi-effective, like negative 0.02 or whatever, maybe we can't actually tell negative 0.02 apart from 0. So it's kind of a debated topic about whether there are any systems with negative chi-effective, which would mean that there are tilts misaligned by more than 90 degrees, which would maybe mean that not everything is evolving from isolated binary evolution. But this is still under debate. And if you want to learn more about this, Simona Miller is a grad student here who has been working a lot about this recently. So you should just ask Simona. Yeah.
So a long time ago, there was a picture that stars and binaries would accrete, and that accretion might spin up the star, and you might expect black holes to have, might spin up the black hole. So you might expect black holes to have large spins of 0.5, 0.6, even 0.9.
Yeah.
Here it looks like chi-effective, which jumps out at me about this is that it looks like a lot of them are like 0.2 or less.
Yes.
So is there something interesting about the fact that these chi-effectives are low?
Yes. I'm going to talk about that in my next slide.
Right.
Yes. Smaller spin magnitudes. Yeah, that is really interesting. So this is very similar to the other plot, but now in terms of chi-effective, this is actually from a model that fits the spin magnitudes and the spin tilts simultaneously, but marginalizing over the spin tilt distribution. So this is just the black hole spin magnitude. And this is what we infer for the binary black holes. So yeah, almost, all the time, the binary black hole spins are smaller than around 0.4, even if we allow them to be kind of isotropic, which would lead to smaller chi-effective, but the spin magnitudes still have to be pretty small. So that's what we infer for binary black holes. And this is unexpected because everything we knew about black hole spins before was from observing for stellar mass black hole spins, is for observing these stellar mass black holes in X-ray binary systems. And you can see that in both low mass X-ray binaries shown here in pink and high mass X-ray binaries shown in blue, the spin magnitude distribution skews to much higher spin tilts. So especially for the high mass X-ray binaries, I mean, we only have 3 of those, so the error bars are big, but they're all the observations are like 0.8 and above. So for exactly as you were saying, for the low mass X-ray binaries, people were saying that low mass X-ray binaries can get their spins through accretion and kind of long-term accretion onto the black hole, because those systems are accreting for a long time. For high mass X-ray binaries, the star that's accreting onto the black hole, it's not actually really accreting, it's kind of wind-fed accretion. And it's a massive star, so it doesn't live for very long. So it's kind of hard for the high mass X-ray binary case to get enough accretion onto the black hole to spin it up. And so usually we think that the spins for high mass X-ray binaries are natal spin. So the spin that the black hole was born with, like right after the star died, which is also what we think for binary black holes. But then why are these natal spins so incompatible? And I'm sort of slow on time, so maybe I won't go into too much detail, but look out for an upcoming paper by Monica Gallegos Garcia, who's a grad student at Northwestern, who's been thinking about kind of differences in the evolutionary pathways that may lead to high mass X-ray binaries and binary black holes, and why it might still be the natal spin of the black hole, but just that the natal spin of the black hole is affected by the earlier stellar evolution and possible evolutionary sequences that can happen in binaries that would spin up the cores of your stars for high mass X-ray binaries, but then those systems won't go on to evolve into binary black holes. Yeah, and so I am running pretty short on time, so I'll just go ahead and just say a couple of things about evolution with redshift, because it's very exciting. And it's one of the things that I think is most exciting, because every time our detectors turn back on, not only are we observing way more events, we're actually observing events that are at higher distances and probing earlier redshift. So that's always something we can look forward to with future upgrades to gravitational wave detectors, is seeing a kind of new population of binary black holes, because we're seeing binary black holes at higher redshifts that merged even longer ago. And so you can see in blue here is our measurement of the merger rate normalized to the merger rate today. So look back time on the bottom axis and redshift on the top axis. And we kind of infer pretty confidently that this merger rate increases as we look out to higher redshifts. As we look back to earlier times, the merger rate a long time ago was higher than it is today. And what we can do is try to compare this to the star formation rate. So we think that the progenitors of these black hole mergers are massive stars. The massive stars have some merger rate, and this is again just normalized to the merger rate today. So the only thing to pay attention to is the shape of this. The star formation rate peaks at around redshift of 2, and then declines pretty steeply out to today. We now think that the progenitors of these black holes are maybe following the star formation rate, but then there's some delay between when the stars formed and when the binary black hole actually merged. And depending on that delay, if that delay is pretty short, then the merger rate will look pretty close to the star formation rate, because it's only off by a short amount of time. If that time delay is very long, then the merger rate will peak at much earlier redshifts and have a much more gradual redshift slope. And so you can see from here that we're already ruling out time delay distributions that have the longest time delays. We actually fit for the time delay distribution. The data is consistent with, everything having very short time delays. There have been no time delays, and we're kind of ruling out that there's a lot of support for these long time delays. And this is interesting because the time delay distribution is telling us about the formation channel. It's kind of telling us about the physics that brought those two black holes to merger. And I will skip over this, but different formation channels make predictions for the time delay distribution. And so that's something that we can compare to theoretical predictions and try to disentangle these formation channels and learn about the physics that's bringing these objects to merger. I'll skip over this, but you can also use the host galaxies if you identify host galaxies to events, and those host galaxies are star forming. Right now, we might think that time delays are short. If those host galaxies are sort of more red and dead, but very massive, we might infer that time delays are long. And there's this nice paper led by Susmita Adhikari that kind of goes into the details of that. And then again, as I was saying, this is very exciting. It's only going to get more exciting in the future. Hopefully we'll have these really fancy next generation detectors that will be able to map the black hole merger rate across all of cosmic time. So these are things like Cosmic Explorer and Einstein Telescope, which you can see here. We're probing a pretty substantial redshift reach already out to redshift 1 or so, but with the current detectors, we won't be able to see mergers past the peak of star formation rate at redshift 2. But with these next generation of detectors, we should be able to see mergers all the way out to the edge of the binary black hole universe, back before there were any mergers. And what we can do from that is also look at the evolution of the mass distribution with redshift, evolution of the spin distribution with redshift. Right now, we're only able to look at it out to redshift 1, but hopefully in the future, we'll really be able to map that across all of cosmic time, which will tell us a lot about formation channels. Okay, so just to quickly conclude, there's a whole lot we can learn about gravitational wave populations. I've only covered a very small amount of it, even though you might be thinking that I talked forever. But just some of the questions that we're starting to answer about how these black holes and neutron stars are made, thinking about these mass gaps, these natal spins. I didn't really talk at all about the mass ratio distribution, but that's super important in thinking about what's the relationship of the two masses in the binary, the relationship between the two spins. Then this kind of setting for where these mergers happen across cosmic time, how does that relate to the star formation rate, the evolution of chemistry in the universe, the metallicity evolution, the host galaxies. And then I didn't talk about this at all, but I'm also very excited about thinking about cosmological implications of these sources and how we can actually use these to measure the expansion of the universe and probe dark energy and think about large scale structure. So with that, I will conclude, and I'm happy to take any additional questions.
Any additional questions? Yes.
So I assume binary black holes also go through a common envelope phase. So do they get short during that phase, and did that spin down their spin?
Yeah, so, oh, right. So the question about how might the common envelope affect the spin of the black hole? Like, can the black holes get torqued during the common envelope phase? I actually don't know much about like angular momentum exchange during the common envelope itself. I mean, it's super complicated to model. And I think the main thing about the common envelope phase is that so I guess for people who aren't familiar, basically during isolated binary evolution, there's a lot of mass transfer, and we think that sometimes the mass transfer might be unstable, which leads to this common envelope. So the donor star is transferring this mass unstably and kind of wraps the whole system in this one common envelope. And then during that, orbital energy can get dumped into that common envelope. And so the common envelope can be ejected and get rid of a lot of the system's orbital energy. And that can kind of be this like magic box almost in bringing the two objects closer together so that when they form a binary black hole, they can merge within the age of the universe. And so the main thing there would be, so you have this, in this scenario, you have a common envelope between a star, the star that's producing the envelope, and a black hole already. And so I don't know if that can torque the black hole in any way, unlike normal accretion. That seems interesting. But what can happen is that after you have a common envelope, now the donor star has lost its envelope. So it's essentially just this helium core at that point, and it's now a lot closer to the black hole. And so that helium core can get tidally spun up. It can be tidally locked onto the black hole and tidally spun up, which could actually lead that second born black hole to have some spin that it got from that tidal locking after the common envelope. Whereas if you don't have common envelope, it's harder to get that tidal spin up because your two objects, your black hole and the star, aren't close enough together to have that efficient spin up in that way. So that's kind of what I know about like how the common envelope affects spin, but it's not directly through the common envelope. So yeah, that's an interesting thing to think about.
Some questions on Zoom.
Oh, yeah.
Sri, do you want to ask your question?
Yeah, the mass distribution, that's all is quite fascinating, and really a unique insight into formation of black holes. However, the story about black holes and their host galaxies, I think, is quite weak in my view. And I say this because it reminds me, so amazingly enough, completely exactly, reminds me of the story of gamma ray bursts. There are two types of gamma ray bursts, collapsars, which come from massive stars. There's clear evidence, and then the mergers, which is the ones which result in neutron stars. So again, the same story here. There's directly born and merged and so on. And there's a lot of hope with GRBs that we'd be able to use them to trace the history of star formation and say something about metallicity. Now, in the case of GRBs, there's a huge advantage they have that simply isn't there for gravitational wave astronomy, and that is they can be localized to arc-second precision, and the host galaxy is actually nailed down. This field, I don't think will be doing any of that stuff for a very, very long time. And even if it did so, I think those are not very interesting questions, actually, that using black holes to trace star formation history. Yeah, this is a very mature field. It's not very clear. This will add a lot. It's a good thing to do. But I think as I said, if you look at the history of GRB host galaxies, and maybe there's someone in the audience who would not be happy with that, I would say we haven't learned much. We got over 100 or a few hundred host galaxies, redshifts. Yeah, and they come from this low luminosity, low metallicity dwarf galaxies. Yeah, it's a little feature, and that's about it.
Yeah. So for the host galaxies, I agree that we're a long way away from host galaxies for black holes. This was actually thinking about host galaxies of neutron stars, of the binary neutron stars, which is, again, you can learn things about the time delay distribution from that, but it's also just useful to build up to having host galaxy statistics also. So like for the future, we know where to look. And if we're trying to get redshifts from host galaxies, we kind of know like which host galaxies to weigh more, like that are more probable hosts and things like that.
Well, but I already know the answer for the neutron star merger. We have a bunch of host galaxies from short bursts, which is reasonably, I would say, established to be coalescent. So you're not going to beat that easily. In fact, the new gamma ray burst missions will accelerate that game. It'll be a very long time before gravitational wave astronomy can compete with short hard bursts at redshift half.
Yeah. I mean, I think that like understanding the relationship between the short gamma ray bursts and the mergers I don't think it's completely like one-to-one well understood. Like there could be some dependence on like the masses of the binary neutron stars and which ones and kind of the gamma ray burst properties. But yeah, I don't think we should be doing this independently with gravitational waves at all. I think the thing about the kind of looking at like the redshift evolution on its own, like this is something that doesn't rely on host galaxies. We're just mapping the black hole population across redshift. And even though, I don't think like we won't be able to use this to measure the star formation rate better than other ways of measuring the star formation rate. We're really only measuring this combination of star formation and time delays. So if someone tells us like this is the low metallicity star formation rate, we know it really well, then that's great, because then we're learning about the time delay distribution for binary black holes, which will tell us directly about the formation channels. But I think we still don't perfectly know the metallicity evolution of the universe, kind of what is the spread of metallicities at different redshifts and the low metallicity star formation rate. And so I think that's something that, again, we should use gravitational waves together with other observations that are giving us access to that. So we can kind of think about what are gravitational waves bringing to that picture.
Yeah, no, I like that plot. The one you're showing is great because this is a fact of the universe. Okay, but I think it's, the host galaxy stuff, it's been there, done that. I think the GW community should move on to more interesting questions. This is not it.
Yeah, well, so this plot we don't have it host galaxies for any of these. This is purely like from the gravitational wave data.
Thanks.
Any more questions on Zoom? Maybe one more. I guess we're after the hour now.
Just one more.
Okay.
Ranga?
Yeah, thanks. It was a thought-provoking talk, regardless of whether or not you agree with it should be used as a star formation history or not, a probe of star formation history or not. But my question was, you focused a lot on the upper mass limit for the black holes, but you didn't say very much about the best fitting slope. So what is the slope that you're getting for the black hole mass function, and how does that compare with, say, taking a standard IMF and putting in some mass loss? What's the slope, first of all?
Yeah, that's a good question. It's kind of hard to answer because it's like, what slope, like which part of this mass distribution actually is well approximated by a power law, and where should we draw that power law? So in this model, there's like some underlying power law distribution. It's the same at these low masses, and at this high masses, it's the same slope, and there's this Gaussian peak on top of it. So if you trust that this is what the universe is doing in making black holes, then this power law slope is pretty steep. I think it's like -2 point something, which is consistent with like the IMF for stars. But it is, yeah, I think I didn't talk very much about the slope because I'm a little skeptical of whether any part of this distribution actually is a power law. And I think I think there's not enough that we really know about the mapping between massive stars and compact object mass yet. That it's, I guess like the dream would be to actually be able to learn about that with the gravitational wave signal, and to actually, measure some power law slope here and map that back to the mass to compact object, the star mass to compact object mass relation. But I think even like on the data analysis side, I'm not sure we're there in terms of identifying the relevant parameter to use for that.
So just to clarify your point there, you're saying that the derived slope, assuming that you can fit it with a power law, which obviously masks are ignorance, but let's say we fit it with a power law, you get -2 point something after correcting for all the volume selection effects, which, where you detect the bigger mass black holes more easily than the smaller mass black holes. Is that right?
Yeah.
Okay.
I think that's right. That's what I remember, but I have to go back to this paper to check for sure.
Okay, thank you.
Great, let's thank Maya again.